So let's look at a reaction coordinate diagram for this process. We start reasonably stable because we're aromatic. It goes up and forms a carbocation, which also has lost aromaticity. And then it goes through to some kind of a product, which is somewhere on the order of the same stability as the starting material. It depends on what the product is. So the intermediate is here. And remember, it's high energy. Even though it's resonance stabilized, it's lost aromaticity. So it's much higher energy than our starting material or our product, which are aromatic. The activation energy is also quite high to get to that point. So that's why we need a very strong electrophile to help this reaction proceed. So let's begin to look at halogenation reactions. As we've already discussed, we cannot add halogen to benzene in an addition reaction. That doesn't work. So if we treat a benzene with just chlorine, it's not strong enough. It's not a good enough electrophile to make this reaction occur. So what we have to do is we have to somehow make the chlorine more reactive. We have to create a better electrophile. So we do that by reacting with chlorine with some kind of a Lewis acid, like iron trichloride or aluminum chloride. So what happens that makes this reaction occur with the Cl2 and the iron trichloride? Since iron trichloride is a Lewis acid, that's the same thing as saying it's an electrophile. So what happens is electrons from the chlorine come over and react with the iron. To make an intermediate, it has a positive charge on chlorine and a negative charge on iron chloride. And this bond actually breaks to form Cl+, our electrophile, and FeCl4-, which eventually will be our base that can take off the proton. So this reaction is the reaction to form our electrophile that we just did. Now we want to look at the reaction of the benzene with the electrophile. So this is the same mechanism that we just learned in the general mechanism, and that is that electrons will come out from the benzene to the chlorine to make an intermediate. This intermediate will react with a base. The base will deprotonate it to reform our aromatic ring. This chapter seems really complex. There are a lot of reactions in this chapter, but really the mechanism of the electrophilic aromatic substitution is always the same. Electrons come out to the electrophile, they form a carbocation intermediate, a base comes and deprotonates, and we get the aromatic ring back. Those steps are always the same. The only difference is what our electrophile is. The reactions that you actually have to learn in this chapter are mostly about how do we form the electrophiles. So the next reaction that we'll look at is a nitration reaction. If we take benzene and react with nitric acid and sulfuric acid, we're able to form nitrobenzene. So how does this happen? So the first thing we need to do is we need to figure out how do we make the electrophile. To do that, we need to know our structures of nitric acid and sulfuric acid. So to understand the mechanism for formation of the strong electrophile in this case, we need to look at the reaction between nitric acid and sulfuric acid. So first what we have to recognize is that sulfuric acid is actually a stronger acid than nitric, so it's going to donate a proton. So one of the electron pairs on the OH and nitric acid will come over and grab a proton from sulfuric acid, pushing that electron pair onto oxygen. And that will make two things. One, it makes this protonated version of nitric acid, and then it makes HSO4-. HSO4- eventually will be our base. The protonated nitric acid can then fall apart because we've got a water molecule here. So if this electron pair leaves and goes on to oxygen, what we get is NO2+ and water. So now we have our strong electrophile, NO2+, we have our base that we'll eventually use in HSO4-, and now we can go through and do our reaction with benzene. You may notice here in the nitric acid, here again in this intermediate, and here where our nitro is attached to our ring, that we have a charge separation with an O- and N+. That's because we can only have 4 bonds to nitrogen. It doesn't have low-lying d orbitals, and it can't have an expanded octet like phosphorus could have. So we can't draw 5 bonds to nitrogen. So that's why these have to have charge separation. The HSO4- then will come back in as the base, grab that proton, and reform the aromatic ring. Just like with the last reaction.